Okay, today we're going to work with reducing radicals. So go ahead and open up your Algebra Review notebook, click on the Radicals tab, and let's look at what it means to reduce a radical. But before we start reducing, let's talk about our radicals in general. When are they perfect and when are they non-perfect? So let's start with our perfect square roots. Think about when you square a number. 1 squared is 1, 2 squared is 4, 3 squared is 9. Think about that list of numbers, and I'm actually going to write them up here at the top, and it would probably be a good idea for you to do the same. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. Those you should pretty well know off the top of your head. I know there's a few others. Past that would be great to memorize at least till 15, if not to 20. That way you don't have to rely on a calculator. You're not having to reduce and think, is it a perfect square or not? So looking here, I see that 81 was on our list. What times itself gave me 81? And that was 9. That's all you have to do here. Now, let's skip 256 and come back to that one in just a minute. Let's go to 1. 1 squared is, or square root of 1 is very easy. It's just 1. And then let's go to the bottom one with a fraction. This one looks difficult, but it's not. Break it into 2 pieces. Think of it in terms of this. Square root of 9 over the square root of 100. Both of those were on our list. The square root of 9 was 3. The square root of 100 is 10. Can I reduce 3/10 down any? No, so that would be it. That's all you have to do. Break it into a numerator and denominator. Now, 256. It's on the perfect page, which means it is a perfect square, but it's not on our list, which means it's higher than 10. So if you're like, I don't know how high to go here, let's do our reducing radical trick, and I'm going to show you something here. So let's take 256 and let's divide it by 2. Okay, that would be 128. 2 is prime. I want prime numbers here. So now let's take 128 and divide it by 2 because it's an even number. We're not thinking about very difficult numbers. We're simply just dividing by 2. Okay, another prime number. 64 can be divided by 2 also, and that gives me 32. 32 can be split. 16 can be split. 8 can be split. And 4 can be split. Now, let's count how many 2's we have here. I see 1, 2, 3, 4, 5, 6, 7, 8. Okay? So I'm going to take that and I'm going to write it like this. There's all my 8 2's that I just highlighted under the radical. I haven't changed the value. If I were to multiply all those 2's together, I would be back at 256. Here's how you reduce. You want to look for pairs. So I have a pair there, a pair of 2's there, pair here, and a pair there. How many pairs is that? 4. Do you see the 4 pairs? 1, 2, 3, 4. There are none left over, which means the radical is now gone. So I bring those 4 2's out, and I'm going to multiply them. 2 times 2 gives me 4, times 2 is 8, times 2 is 16. So again, if you don't know a perfect square root, you're going to have to do the trick this way. And that's how we're going to reduce our non-perfect radicals here in just a minute. But if you had memorized those, we could have just set at 16 and been done. Okay, so there's your couple options when they're perfect. Now, let's look at this list. None of those numbers were on our list. So we're going to have to do the breakdown trick like we just did and break these numbers down. You can think of any factor pair that goes into 48. 4 and 12, 6 and 8, 2 and 24. Any of those work. It's your choice. It will all end up being the same answer. I'm going to choose, let's go 6 and 8. Okay, are 6 and 8 prime numbers? No, which means they break down. And so 6 breaks down to a 3 and a 2, and we know those are prime. I like to circle my prime numbers because that tells me I'm done with that. It's stopped. I don't have to worry about my tree anymore there. 8, I can break down into 2 and 4. 2 is prime, but 4 is not. So let's break that down into 2 and 2. All of those are prime. So I'm going to take all 5 of my circled numbers and put them under the radical. I like to group mine. So I have a 3 and then I have 4 2s. Remember what I said on the 256 problem. We want to look for pairs. 3 does not have a pair, which means it's going to stay under the radical. But I have 1 pair of 2s, 2 pair of 2s. So I'm going to bring those guys out to the front and say 2 times 2 times the square root of 3. So this pair of 2's went there, that pair of 2's went there. Because 2 times 2, if you think of it like this, 2 times 2 is 4, the square root of 4 is 2. That's why you're only bringing one 2 out and not both of them, because you are still square rooting. Now I can combine what's on the outside and say 4 square root of 3. And that is the square root of 48 simplified or reduced. Okay, let's go to the next one. 72, again, several different options to start with. I'm just going to go 8 and 9. Neither one is prime, so let's keep breaking down. 8 can break down into 4 and 2. 2 is prime. 4 breaks down into 2 and 2. All of that side is done. Now let's go to the 9. 9 breaks down 3 and 3. 3's are prime, meaning nothing but itself and 1 can be broken down into it. So everything is circled at this point, nothing left to break down. Let's put all of those numbers under our radical. We have 3 2's that we circled and 2 3's. Okay, let's look for groups. I have 1 pair of 2's, 1 pair of 3's. This guy here doesn't have a pair, so he's going to stay under the radical. So we have a 2 that comes out times a 3 that represents each of our pairs times the square root of 2 because he didn't have a pair. Multiply what's on the outside, and that gets me 6 square root of 2. Okay? Let's look at the next one. 162. So it's kind of a big number. We probably don't know a factor pair off the top of our head, but it does end in an even number, which means it's divisible by 2. So that's an easy way for you to start if you can't come up with something. So 2 times 81 gives me 162. 2 is prime, 81 is not. Break it down. Let's say 9 and 9. 9's are not prime. Break those down. But all those 3's will be. So nothing left to factor. Let's bring all those numbers under the radical. I see 4 3's and a 2. Again, you can put those numbers in any order. I just like to keep mine organized so that I can look for pairs. 2 doesn't have a pair, but I have 2 pairs of 3's. So where do those pairs go? On the outside. I have 2 3's that are going to go on the outside, and I'm left over with that 2. Multiply what's left over, or what's on the outside. That gives me 9 square root of 2. Okay. Last one here, 117. It doesn't end in a even number, so it's not divisible by 2. So let's keep thinking here. Try a 3, try a 4. One of the rules that I remember is if you add the digits together, what I mean by adding them together, 1 plus 1 plus 7, that equals 9. Is 9 divisible by 3? Yes, so it is divisible by 3. Then I can divide it, and that gives me 3 times 39. If you don't know those rules, that's okay. Get a calculator, get a pen and paper, start dividing by random numbers. If it doesn't go by 2, try a 3, try a 4. You know what's divisible by 5 and 10. Those are easy. Just start dividing. 3 is prime. Stop there. 39 is not. 3 times 13. We already said 3 is prime, and so is 13. Nothing left to factor. Take it under the radical. 2 3s and a 13. Do we have any pairs? Yeah, we have a pair of 3s. Where do our pairs go? On the outside. So I have a pair of 3s on the outside. One pair of 3, which means when I say that, I mean that just means 1 3 goes on the outside. And we're left with a 13. Nothing to combine. And that gives us our reduced radical. You're going to need to know how to do this for when we get into the distance formula and things like that. So please